For the automatic closed-loop engine cooling control system shown in the figure, A. Identify the signal paths A, B, and C. B. Describe the function of the comparator. C. Name and describe the function of component D. And D. State a suitable device capable of producing a varying signal at T. A. Signal paths. Path A. This path carries the coolant temperature signal from the temperature sensor to the comparator. Path B. This path carries the control signal from the comparator to the cooler fan. Path C. This path carries the control signal from the temperature sensor via the controller to the electrically controlled three-way valve. B. Comparator function. The comparator compares the coolant temperature signal, path A, with a reference voltage, set point temperature. If the coolant temperature is higher than the set point, the comparator puts out a high signal to path B. This high signal activates the cooler fan to start cooling the engine. When the coolant temperature reaches the set point, the comparator outputs a low signal, turning off the cooler fan. C. Component D and its function. Component D is an electrically controlled three-way valve. It provides variable flow control. D. Device at T for varying signal. A suitable device capable of producing a varying signal at T would be a temperature sensor. This sensor would convert the engine oil temperature into an electrical signal. This signal could then be used to adjust the set point temperature of the comparator based on the engine's operating conditions. This would allow for more dynamic and efficient cooling control. A. State the relationship between proportional band and gain. B. The figure shows the level in a water tank that is being controlled by a float and lever proportional system. 1. Describe how the gain of the control system can be increased and decreased. 2. Describe what happens when the flow out is increased. 3. Describe the effect of increasing the controller gain with respect to the steady state tank level when the outflow is increased. 4. Describe how the introduction of integral action would affect this system. A. Relationship between proportional band and gain. Proportional band, PB, and gain are inversely proportional to each other. This means that as the PB increases, the gain decreases, and vice versa. Mathematically, it can be expressed as gain equals 1 over PB expressed as a percentage. For example, if the PB is 20%, the gain is 5. 100 divided by 20 equals 5. Conversely, if the gain is 3, the PB is approximately 33%. 100 divided by 3 equals 33%. B. Level control in a water tank. 1. Increasing and decreasing gain. In the given lever system, the gain can be adjusted by modifying the length of the lever arm. A shorter lever arm increases the gain because a smaller movement of the float translates to a larger movement of the control valve, resulting in a more significant response to level changes. Conversely, a longer arm decreases the gain as a larger movement of the float produces a smaller movement of the valve, leading to a less pronounced response. 2. Increased flow out. When the flow out of the tank increases, the water level will start to drop, the float will move down, and the lever will pivot, opening the control valve further to allow more water inflow. However, with a proportional only system, the valve opening will only reach a point where the inflow matches the increased outflow, and the water level will stabilize at a new, lower level. 3. Increasing gain with increased outflow. Increasing the gain by shortening the lever arm in this scenario will make the system more responsive to level changes. The valve will open wider for smaller float movements, attempting to compensate for the increased outflow more aggressively. However, this can lead to hunting, where the water level oscillates around the desired level due to the system's overreaction. 4. Introducing integral action. Adding integral action to the system can help address the limitations of proportional control. The integral term essentially remembers the past level deviations and continuously adjusts the valve position to eliminate them. This helps the system reach and maintain the desired level even with changes in outflow, reducing hunting and improving steady state accuracy. Remember that the specific behavior of the system will depend on various factors like the tank size, flow rates, and valve characteristics. A. Identify components A, B, C, D, E, F, G, and H shown in the figure. B. Explain the difference between a strainer and a filter in a hydraulic circuit. A. Component identification. A. Pressure gauge. B. Hydraulic motor. C. Relief valve. D. Directional control valve. E. Filter. F. Reservoir. G. Pump. H. Strainer. B. Strainer versus filter in hydraulic circuits. While both strainers and filters remove contaminants from a hydraulic fluid, they differ in their level of filtration and purpose. A strainer. Its function is to remove large particles like dirt, debris, and metal chips to protect pumps and other sensitive components from damage. Its micron rating typically has a larger micron rating of 500 to 200 microns, allowing smaller particles to pass through. Cleaning. Usually cleaned periodically by removing and emptying the collected debris. A filter. Its function, it removes finer particles and contaminants that could cause wear and tear on components. Its micron rating is a smaller micron rating, 10 to 25 microns, to capture smaller particles than strainers. Cleaning may be replaceable or cleanable, depending on the type. In essence, a strainer acts as the first line of defense against large debris, while a filter provides finer filtration for optimal system protection. The figure shows a tank filling with liquid at a variable rate and an output regulated manually by an operator controlling a value. Explain, with the aid of a control block diagram, the control process taking place that enables the operator to maintain a constant tank level, H, for varying rates of fluid flow input. Note, fluid flow in will always be less than the maximum flow out with the valve fully open. The image shows a tank with a variable flow input and an outlet valve manually controlled by an operator. The tank level is measured by a sight glass. The control process. 1. Measurement. The operator observes the tank level through the sight glass, visually measuring the current level, H. 2. Feedback signal. The observed level serves as the feedback signal for the operator. 3. Comparison. The operator compares the observed level, H, with the desired level, set point, which is usually indicated on the sight glass or known based on operational requirements. 4. Error calculation. The operator mentally calculates the difference, error, between the current level and the set point. 5. Control action. Based on the error, the operator adjusts the hand wheel of the valve, opening it more to increase inflow, positive error, or closing it partially to decrease inflow, negative error. 6. System response. The change in valve openings affects the inflow rate, causing the tank level to rise or fall. 7. Adjustment. The operator continuously monitors the level and adjusts the valve opening as needed to maintain the desired level. Additional notes. In this manual system, the operator acts as both the controller and the actuator, making adjustments based on their visual observation and judgment. The accuracy of level controls depends on the operator's skill, experience, and ability to react to changes quickly. This system is relatively simple and inexpensive, but it can be challenging to maintain precise level control, especially with varying flow rates. For more accurate and automated control, an electronic level controller and an actuated valve could be implemented. A. Describe, with the aid of a control block diagram, how a governor maintains the speed of a diesel engine driving a generator. B. Describe the reasons for integrating the error signal and the effect it has on the governor fuel rack. The governor in a diesel engine driving a generator maintains the engine speed by regulating the fuel supply based on sense deviations from the desired speed. Here's the control block diagram with its components and functions. Speed sensor measures the actual engine speed, feedback signal. Governor, the controller, compares the measured speed with the desired speed, set point, and calculates the error. Error is the difference between actual and desired speed. Gain amplifies the error signal to adjust the fuel rack position effectively. Fuel rack regulates the amount of fuel delivered to the engine cylinders. Fuel injector injects fuel into the cylinders based on the rack position. Set point represents the desired engine speed, often adjustable based on generator load. Engine load, external disturbance affecting the engine speed, e.g. increased electrical demand. B. Integrating the error signal. Governors often incorporate integral action to improve speed regulation. Reason: constant speed deviations, steady state errors, can occur with proportional, i.e. gain control alone. The governor might react to the initial error, but may not reach the set point perfectly, especially under varying loads. The effect: integrating the error signal accumulates the error over time, providing a larger correctional signal until the error is eliminated. This helps the governor remember past deviations and adjust the fuel rack further to reach the exact set point even with external disturbances. Impact on the fuel rack. Integrating the error results in a gradual, sustained adjustment of the fuel rack towards the required position. This ensures the engine speed converges to and maintains the desired value, overcoming steady-state errors. In summary, the governor uses a feedback loop with error correction and amplification to regulate the fuel supply and maintain the engine speed despite load changes. Integration improves the system's ability to eliminate steady-state errors and achieve precise speed control. A. Sketch a block diagram of a split range control system used to control the jacket water temperature of a main engine. B. Describe the operation of this system. A. Block diagram. Here is the block diagram of a split range control system for jacket water temperature. Components and functions. Temperature sensor measures the jacket water temperature. T jacket. Controller split range receives the temperature signal and compares it to two set points. Set point low, minimum desired temperature, T min. Set point high, maximum desired temperature, T max. Calculates separate errors for each set point. Uses separate gains for each error, gain low, gain high, and generates two output signals based on the errors and gains. Cooling valve opens or closes based on the low range output signal to regulate cooling water flow. Heating valve optional opens or closes based on the high range output signal to regulate heating water flow if needed. Bypass valve optional allows bypassing the cooler or heater when necessary. B. System operation. Temperature measurement. The sensor continuously measures the T jacket. 2. Error calculation. The controller compares T jacket with both set points, T min and T max. If T jacket is below T min, a positive error occurs for the low range control. If T jacket is above T max, a positive error occurs for the high range control. If T jacket is within the desired range, where T min is less than T jacket is less than T max, both errors are 0. Output signal generation. The controller uses separate gains, gain low and gain high, to amplify the calculated errors. The low range output signal controls the cooling valve. Higher error, T jacket below T min, opens the valve more for increased cooling. Lower error, T jacket closer to T min, closes the valve partially. The high range output signal controls the heating valve if present. Higher error, T jacket above T max, opens the valve more. Lower error, T jacket close to T max, closes the valve partially. The bypass valve might be used to avoid unnecessary operation of the cooler or heater when T jacket is within the desired range. System response. The control valve openings adjust the cooling or heating water flow, affecting T jacket. The system continuously monitors and adjusts to maintain T jacket within the desired range despite disturbances. The specific gains and set points are chosen based on engine requirements and operating conditions. Explain each of the following control terms. A. Settling time. B. Repeatability. C. Dead zone. D. Hysteresis. E. Proportional bandwidth. A. Settling time. Settling time refers to the time it takes for the output of a control system to reach and stay within a specified percentage, usually 2% or 5%, of its final value after a step change in the input or a disturbance. It reflects the system's responsiveness and ability to stabilize around the desired operating point. A shorter settling time indicates faster response and better disturbance rejection. B. Repeatability. Repeatability refers to the consistency of a control system's output for repeated applications of the same input under identical conditions. A highly repeatable system produces essentially the same output every time it encounters the same input, demonstrating consistent and reliable behavior. Dead zone. The dead zone is a range of input values around the set point where the controller produces no output change. In other words, even if the input deviates slightly from the set point within the dead zone, the control system remains inactive. This can be intentional to avoid unnecessary actuator movements for minor fluctuations, but it can also lead to sluggish response and steady-state errors if the dead zone is too large. D. Hysteresis. Hysteresis is a phenomenon where the output of a control system depends not only on the current input value, but also on the history of the input. It creates a different response for increasing and decreasing input values around the set point, resulting in a staircase effect. This can be desirable in some applications for switching actions, e.g. a thermostat, but it can also cause oscillations and limit control accuracy. E. Proportional bandwidth, PB. Proportional bandwidth, PB, is a measure of the range of input values that will produce the full output range of a proportional controller. It is expressed as a percentage of the set point and is inversely proportional to the controller gain. A higher PB means a smaller gain, resulting in less sensitive but more stable control. Conversely, a lower PB indicates higher gain, leading to more responsive but potentially less stable behavior. A. Explain each of the following control terms. 1. Proportional bandwidth. 2. Integral action. 3. Derivative action. B. Describe a 3-step method for tuning a PID controller. A. Control terms. 1. Proportional bandwidth, PB. Proportional bandwidth, PB, refers to the range of input values around the set point that will cause the proportional controller's output to span its entire range. It can be expressed as a percentage of the set point and is calculated as the inverse of the proportional gain, Kp. So Pb is 100 divided by Kp. A higher Pb corresponds to a smaller gain, meaning the controller reacts less aggressively to input changes, leading to slower but more stable behavior. Conversely, a lower Pb signifies a higher gain, resulting in faster response, but potentially causing oscillations if not tuned properly. 2. Integral action. Integral action, also known as reset or I action, accumulates the error over time and contributes an additional term to the controller output based on the integral of the error signal. This helps eliminate steady-state errors that proportional control alone might not address. The integral term gradually increases the output as long as the error persists, eventually bringing the output to a value that cancels out the error. The integral gain, Ki, determines how quickly this adjustment occurs. Too high a value can lead to overshoot and instability, while too low a value might leave steady state errors uncorrected. 3. Derivative action. Derivative action, also known as D-rate or D-action, considers the rate of change of the error signal and adjusts to the controller output accordingly. This helps to anticipate future changes and provides faster response to transient disturbances. The derivative term adds a component to the output proportional to the rate of change of the error. The derivative gain, Kd, determines the sensitivity to error rate. High values can lead to excessive control action and instability, while low values might cause sluggish response. B. 3-step PID tuning method. 1. Start with proportional control only. Set Ki and Kd to 0. Increase the proportional gain, Kp, gradually until the system starts to oscillate. Note the value of Kp at which oscillations begin, P-osc. Reduce Kp to approximately 50% of P-osc to achieve a stable but oscillatory response. Introduce integral action. Increase the integral gain, Ki, slowly while observing the system response. The integral term will gradually eliminate the steady-state error introduced by the proportional control alone. Stop decreasing Ki when the response becomes sluggish or overshoots significantly. Fine-tune with derivative action, optional. If further response improvement is desired, introduce derivative action cautiously. Increase the derivative gain, Kd, slightly while monitoring the system's stability. The derivative term can help dampen oscillations and improve transient response, but avoid excessive values that might cause instability. A. Define each of the following terms. 1. Cascade control. 2. Split range control. B. Describe possible problems associated with split range control used for the control of a main engine cooling system. Cascade control. Cascade control involves nesting 2 or more feedback loops to regulate a single process variable. The outer loop, primary loop, sets the desired value for the inner loop, secondary loop. This enables precise control and improved stability by responding to disturbances affecting the manipulated variable directly in the inner loop. 2. Split range control. Split range control uses a single controller with multiple outputs to manage a process variable that needs different control strategies depending on its operating range. Each output controls a separate actuator, typically responsible for heating or cooling the process. B. Problems with split range control for main engine cooling. 1. Interaction between heating and cooling. Coordinating the heating and cooling systems through a single controller can be challenging, especially during transitions between heating and cooling modes. Improper tuning could lead to overshooting, hunting, or instability. 2. Dead zone issues. Each output might have a dead zone, creating a small range around the set point where neither heating nor cooling occurs. This can cause sluggish response and temperature deviations if the dead zones are too large. 3. Complexities in tuning. With multiple outputs and set points, tuning the controller gains and dead zones becomes more complex. Finding the optimal settings for both heating and cooling simultaneously can be time-consuming and require expertise. 4. Potential for single-point failure. A single controller failure could disrupt both heating and cooling, compromising engine safety and performance. 5. Limited applicability. Split range control might not be suitable for all engine types or operating conditions. Some engines might require more flexibility or independent control of heating and cooling, making another control strategy more appropriate. Alternatives to split range control. 2 separate PID controllers. This offers independent control of heating and cooling with simpler tuning but requires more hardware and coordination. Fuzzy logic control. This can handle more complex relationships between variables and operating conditions but requires expertise in fuzzy logic implementation. Overall, a split range control can be a cost-effective solution for basic engine cooling control. However, its limitations and potential problems should be carefully considered before implementation, and alternative control strategies might be better suited for specific environments. A. Explain the term fail-safe in a control system, stating 2 examples where this term is applied. B. Explain the term fail-set in a control system, stating 2 examples where this term is applied. C. State what is meant by a 4-to-3 control valve. A. Fail-safe. In a control system, fail-safe refers to the design and operation of the system in a way that minimizes damage or risk when a component failure occurs. This ensures the system transitions to a known safe state even when unexpected malfunctions happen. Examples: emergency shutdown in chemical plants. If a sensor detects a hazardous gas leak, the system immediately activates the emergency shutdown sequence, safely isolating the leak and preventing further danger. 2. Aircraft engine thrust reduction. If an engine failure is detected, the system automatically reduces thrust on the affected engine, maintaining flight stability and minimizing the risk of a crash. B. Fail-set. Fail-set refers to the behavior of a system where, upon component failure, the system remains in its current state. While not actively transitioning to a safe state, this approach may be acceptable in specific situations where maintaining the current state is preferable to an uncontrolled change. Examples: 1. Room temperature control. If the thermostat fails, the heating or cooling system might remain in its last active state, on or off, maintaining the room temperature until manual intervention. 2. Traffic light signals. If a power outage occurs, the traffic lights might stay in their last illuminated state, red, green or yellow, until power is restored, providing static information to drivers. Important note: fail-set is generally less desirable than fail-safe, as it doesn't guarantee a safe outcome in all failure scenarios. Its use should be carefully considered and only implemented if a fail-safe approach is impractical or poses additional risks. C. 4-to-3 control valve. This refers to a control valve whose stroke or travel distance relates to its flow area change And this characteristic leads to two key features. 1. High flow sensitivity at low openings. Small changes in stem position near the closed position result in significant changes in flow, making the valve suitable for precise control at low flow rates. 2. Limited flow gain at high openings. As the valve opens its fully open position, further stem movement has a reduced impact on flow rate, providing a degree of self-regulation and preventing excessive flow overshoot. Applications: high precision flow control in chemical processes, throttle control in engine fuel systems, dosage control in medical equipment. Remember, the specific advantages and drawbacks of a 4-3 control valve depend on the intended application and its control requirements. With reference to hydraulic governors fitted to alternators designed to run in parallel. A. Explain why these governors have adjustable integral action. B. Explain, with the aid of a load frequency diagram, how two generators operating in parallel are able to achieve a stable load share with a 50-50 ratio. A. Adjustable integral action. Hydraulic governors in parallel alternators have adjustable integral action for two main reasons. 1. Eliminating steady-state speed errors. In a system with multiple generators sharing a load, slight differences in governor characteristics or mechanical imperfections can lead to steady-state speed errors between generators. Integral action in the governor accumulates the error signal over time, gradually adjusting the fuel supply until the speed error is eliminated. This ensures all generators maintain the same speed, synchronism, regardless of minor variations, promoting stable parallel operation and load sharing. 2. Achieving desired droop characteristics. In parallel operation, governors are configured with a specific droop characteristic. This refers to the decrease in generator speed with increasing load. Adjustable integral action allows fine tuning of the droop, which determines how much each generator contributes to the total load change. By adjusting the integral gain, engineers can achieve the desired load sharing ratio between generators, such as a 50-50 split. B. Load frequency diagram and 50-50 load sharing. A load frequency diagram helps visualize the behavior of generators in parallel operation. Here's how two generators achieve a 50-50 load share. 1. Initial conditions. Let's assume both generators share the total load equally, 50% each, and operate at the nominal frequency F0. This point is represented by the intersection of the individual generator droop curves, G1 and G2, with the total load line, P tot. 2. Load change. When the total load increases, P tot increases, both generators experience a slight decrease in speed due to their inherent droop characteristics. The speed drop is larger for the generator with a steeper droop curve, greater integral gain. 3. Integral action and load sharing. The integral action in each governor integrates the speed error over time. In response, the governor with the larger speed drop adjusts its fuel supply more significantly, causing its frequency to recover faster and take on a larger share of the increased load. The other generator's frequency recovers slowly, resulting in a smaller load increase. 4. Equilibrium. This process continues until a new equilibrium is reached where the speed difference between generators is minimal and they share the increased load according to their droop characteristics. With properly adjusted integral gains, both generators can achieve a 50-50 load share at the new operating point. Here's the diagram. We're looking at two downward sloping curves, G1 and G2, representing the droop characteristics of generators. A horizontal line, P tot, represents the total load. The intersection of these lines represents the operating points at different load levels. When the load increases, both curves shift down, but the one with the higher integral gain shifts more, leading to a new equilibrium point where the load is shared equally. With reference to engine governors, explain each of the following terms. A. Sensitivity. B. Hunting. C. Speed droop. D. Stability. E. Isochronous governing. A. Sensitivity. Sensitivity in an engine governor relates to the responsiveness of the governor to changes in engine speed. A highly sensitive governor reacts quickly to even small speed variations, adjusting fuel delivery promptly to maintain speed stability. However, excessive sensitivity can lead to hunting, so achieving the optimal balance is crucial. B. Hunting. Hunting describes an undesirable oscillation in engine speed caused by an overly sensitive governor. The governor overreacts to minor speed deviations, leading to adjustments in fuel supply that overshoot the correction needed. This creates a feedback loop where corrections become too large, causing speed to swing back and forth around the desired value. C. Speed droop. Speed droop is a fundamental characteristic of most engine governors. It defines the relationship between engine speed and load. As the load on the engine increases, the governor allows the engine speed to decrease slightly. This intentional droop ensures stable load sharing between multiple engines operating in parallel on a common bus. Without droop, load changes would cause large speed variations and unstable operation. D. Stability. Stability in an engine governor refers to the system's ability to maintain the desired engine speed despite external disturbances or load changes. A stable governor minimizes speed fluctuations and quickly returns to the set point after any transient event. Various factors, including governor sensitivity, droop settings, and control algorithms, contribute to achieving stable governor performance. E. Isochronous governing. Isochronous governing, also known as constant speed governing, aims to maintain engine speed exactly at the set point, regardless of load variations. Unlike governors with droop, an isochronous governor completely compensates for load changes by adjusting fuel delivery to keep the speed constant. This is desirable for applications requiring precise and constant speed, such as generators supplying critical equipment. However, Isochronous governors may require more complex control algorithms and can be less tolerant of disturbances compared to droop governors. A. State the reasons for fitting a pneumatic process valve with each of the following. 1. A volume booster. 2. A feedback positioner. B. State, with reasons, the type of actuator fitted to the process valves for each of the following systems. 1. A fuel supply system in which the valve must not move on loss of power to the control system. 2. A lubrication oil cooling system in which the valve diverts the oil through a cooler. Reasons for fittings. 1. Volume booster. Increases air flow rate. A volume booster amplifies the low flow pneumatic control signal from the controller to provide a high flow output to the actuator. This is necessary when the actuator has a large volume or requires significant force to operate, which a standard control signal might not be able to provide effectively. Faster valve response. By increasing the airflow rate, the booster speeds up the actuator's response to control signals, leading to faster process adjustment and improved system dynamics. 2. Feedback position. Feedback position improves accuracy and stability. A positioner measures the actual valve position and compares it to the desired position from the controller. Any deviation triggers the positioner to adjust the air pressure to the actuator, ensuring the valve reaches the exact desired position, even if external forces or friction affect it. This significantly improves control accuracy and reduces steady state errors. Overcomes friction and disturbances. Positioners compensate for frictional forces in the valve mechanism and external disturbances affecting the valve movement, ensuring the valve responds faithfully to the control signal despite these challenges. B. Actuator types and reasons. 1. Fuel supply system. Fail-safe operation. Spring to close actuator. Ideally, this actuator would close the valve, stopping the fuel flow, when air pressure fails due to a control system outage. This provides a fail-safe mechanism to prevent uncontrolled fuel release, ensuring safety and system integrity. 2. Lubrication oil cooling system diversion valve. Double acting actuator. This actuator uses air pressure in both directions, open and close. In case of air pressure loss, the valve would stay in its last position, maintaining the current oil flow path, either through the cooler or bypass, depending on the valve state before failure. This avoids uncontrolled changes in oil flow that could affect lubrication and engine health. The specific choice of actuator and accessories depends on various factors like process requirements, safety considerations, and control performance objectives. Some applications might require specific valve designs or fail-safe features beyond the basic categories mentioned here. With reference to an impeller type flow meter, describe how an output is produced and processed to provide each of the following. A. An analog output in litres per minute. B. A digital output in litres per minute. A. analog output, liters per minute. 1. Impeller rotation. As fluid flows through the meter, the impeller rotates at a speed proportional to the flow rate. The impeller blades are designed to minimize drag and ensure consistent rotation with flow changes. 2. Magnetic coupling. The impeller shaft is coupled to a magnet inside the meter housing. This magnet rotates with the impeller, creating a changing magnetic field around it. 3. Pickup coil. A stationary pickup coil positioned near the rotating magnet senses the changing magnetic field. This induces a voltage signal in the coil whose frequency is directly proportional to the impeller rotation speed and hence the flow rate. 4. Signal conditioning. The induced voltage signal from the pickup coil is typically weak and noisy. Electronic circuitry amplifies and filters the signal to remove noise and ensure a clean, reliable representation of the flow rate. 5. Scaling and calibration. The conditioned signal is then scaled and calibrated based on the meter's specific characteristics. This converts the signal voltage into an analog voltage proportional to the flow rate in liters per minute, LPM. The scaling factor is determined during the meter's calibration process using known flow rates. 6. Analog output. The resulting voltage signal, representing the flow rate in liters per minute, is available as the analog output of the flow meter. This can be directly connected to an analog to digital converter, ADC, for further processing, or used directly in analog control systems. B. Digital output of liters per minute. 1. Signal conditioning. Similar to the analog output, the induced voltage signal from the pickup coil is amplified and filtered. 2. Frequency to digital conversion. Instead of scaling the signal directly, a frequency to digital converter, FDC, is used. This chip measures the frequency of the signal, which is directly proportional to the impeller rotation speed and flow rate. 3. Microprocessor and calculations. The FDC signal output, representing frequency, is fed into a microprocessor within the flow meter. The microprocessor uses the meter's calibration data and internal algorithms to convert the frequency data into a flow rate value in liters per minute, LPM. 4. Digital output. The calculated flow rate in LPM is available as the digital output of the flow meter. This can be displayed on the meter itself, transmitting through serial communication protocols, or used for digital control systems. In both cases, the impeller rotation serves as the basis for flow measurement. However, the processing and interpretation of the signal differ, resulting in either an analog voltage or a digital flow rate value as the output. A. Define the term proportional action. B. Explain the purpose of integral action. C. Describe a possible effect of excessive integral action. D. Explain the purpose of derivative action. E. Describe the effect of excessive derivative action. A. Proportional action. Proportional action, also known as P action, is the fundamental component of a PID controller. It directly adjusts the controller output based on the error between the desired set point and the measured process variable. The output change is proportional to the error magnitude, with a higher error leading to a larger output change. This creates a corrective effect, driving the process variable closer to the set point. B. Integral action. Integral action, also known as T action, aims to eliminate steady-state errors. It continuously integrates the error over time and adds this accumulated value to the controller output. This means that even small, persistent errors contribute to the output, eventually forcing the process variable to reach the set point even if the proportional action alone is insufficient. C. Excessive integral action. While beneficial for correcting steady-state errors, excessive integral action can have drawbacks. Overshoot. The integral term's influence might grow too large, causing the controlled variable to rapidly overshoot the offset point before settling down. This can lead to oscillations and instability in the system. Slow response. Excessive integral action can slow down the system's response to transient changes. The integrator focuses on accumulated errors, partially and potentially neglecting sudden changes requiring quicker adjustments. D. Derivative action, also known as D action, anticipates future changes in the error based on its rate of change. It adds a component to the controller output proportional to the derivative of the error signal. This helps the controller react quickly to changing trends in the error, preventing large deviations from the set point. E. Excessive derivative action. Noise sensitivity. The derivative term amplifies high-frequency noise in the error signal, leading to an erratic controller output and control instability. Chattering. If the derivative action is too strong, it can cause the controller output to oscillate rapidly around the set point, even in the absence of significant errors. This phenomenon is known as chattering.